Let's see, it's about an hour long.
Look at all the flashes.
Yeah, and he hated flash bulbs. He told everybody not to take pictures. He told everybody not to take pictures. He hates flash bulbs, or hated flash bulbs.
It was made popular about 20 years ago by a progressive jazz singer named Jim Christie. Words of the song start out, somewhere there's music, how faint the tune, somewhere there's heaven, how high the moon. And the point is that people wondered for a long time just how high the moon is. It's had a great deal of influence on how we thought. And the songs we sang to each other. But how high the moon is something more than just romance. Throughout the history of science, it's been used in understanding our entire universe. I think I'd like to go back a little way in time to the first gentleman I know of that tried to understand the moon in some detail. The gentleman's name was Aristarchus of Samos. And we know he was interested because it was well recorded by a very reliable poet of his named Aristotle. Aristarchus maintained that the sun was the center of the universe. It's a view that was more or less forgotten or perhaps covered up for the next 16 centuries till the time of Nicholas Copernicus, just 500 years ago this year. 16 centuries. Aristarchus had made a really magnificent effort to determine the size of the solar system. And I'm going to use the blackboard a little bit, and I recognize that some of you in the back can't see the blackboard, and so I'll try to help where I can so that you can understand the point we're making. Aristarchus believed in trigonometry and simple geometry. He said there was something to be learned at the time the moon was in quadrature. That's when the moon is just precisely a half moon. That is when the moon looks like this.
Oh, she finds all them other things. I got a bunch of fucking questions.
Now, when we're to go up above the plane of the Earth's motion and look down on the Earth and the moon, we would also see a half moon the same way. And the Earth would be down here. And a person looking at the moon, standing on the surface of the Earth, would see this view of a half moon. That would mean that the sun would have to be out here, like this, with its rays shining outward. And the triangle to which Aristarchus addressed himself was the Earth, Sun, Moon triangle. So at the time of quadrature, half moon, this angle was precisely a right angle. When you had a right angle triangle, you could determine all the measurements of that triangle if you knew just one and measured one angle. He said that this angle was one that the only angle the one the man on the moon could measure was this angle between the Earth and the Sun. Then he said if you knew the distance from the Earth to the moon, you could figure out all the rest of the geometry. And he did precisely that. He measured the angle, and he got a value of 87 degrees, time and a half minute. And establishing the Earth-Moon distance may have seemed to be pretty easy to a gentleman with the giant of intellect that Aristarchus had. And he was interested in those particular times that are just equivalent to the time that we're approaching tonight, the time of eclipse. He wasn't really interested in the kind of eclipse that we're going to see. He was interested in the time when the Earth's shadow passed over the moon. And he noted that during that kind of eclipse, the shadow of the Earth on the moon was a circle. He inferred from that the Earth was round. And he figured that if the sun were an infinite distance away, then the light rays would be parallel, and one could get, if you knew the Earth's radius, you could calculate the lunar radius. He also knew that the sun's rays weren't just parallel, but they toned down in shadow behind them into about a half degree, and he took that into account. All he needed was the radius of the Earth. Now, if you'll remember, a lot of you remember the statistics particularly, that was computed by one of his fellows named Ed, who measured the length of a shadow on the same stick at two different places, Siam and Alexandria, as I remember. He calculated the radius of the Earth as 3,950 miles. Actually, he calculated it 80, but I don't know how long that is. So anyway, he got the value just about right. And Aristarchus, using that value in his measurement of 87 degrees, came in with the fact that the moon was 10 Earth radii, or 40,000 miles, something like that, to the moon, which was wrong. And calculated the Earth distances, or the Earth-Sun distances, being 20 times the value to the moon, which again was wrong. The mistake he made was the angular measurement of the moon as seen from Earth. Now, we all know, particularly eclipse watchers, all know that the Earth and the Sun, fortunately enough, make eclipses because they have the same apparent diameter in the sky, namely 1/2 degree, and that allows the moon to completely dominate the sun. But Aristarchus, when he made his calculations, assumed it was 2 degrees. Now, why he made that terrible error was forever lost to us. But because he made that error, he got the wrong answer. About 100 years later, there was a more careful measurer named Hipparchus. And Hipparchus made the same measurements, and he got a value of a distance to the moon of 59 Earth radii, and 59 times 3,900 is about the right number. He was very close. He also made some other outstanding calculations. He discovered that the moon wasn't the same distance from Earth all the time. It varied. He got the eccentricity, and he found that the moon's orbit was not parallel to the Earth's orbit. It had an inclination, and he measured that. He measured the motion of the nodes, or the intersection between the planes with time, and he measured the motion of the line of epsize, or the change the motion of those points where it's farthest away from the Earth and closest to the Earth. They really did some remarkable amateur astronomy. And then nothing much happened for a long time. After that, centuries went by, and the Dark Ages went by, and nobody learned anything past Hipparchus until the 16th century. And then a bunch of gentlemen came along: Copernicus, Tycho Brahe, Kepler, Newton, Galileo, and they just broke all science apart. Things they found out. Newton found the moon pretty handy. In fact, he depended on the moon to come up with his observations and conclusions about gravity. He quoted, he said, and I quote, "I compared the force requisite to keep the moon in her orb with the force of gravity at the surface of the Earth and found them answer pretty nearly." Or what he said was, the moon, in fact, can tell us a good deal about the gravity here at the Earth. So it confirmed his theories. Well, since that time, in the time of the telescope, a lot of people have made measurements of the moon. They measured optical parallax and the angle between the Earth and the moon at different times. Stellar occultations, that is the time at which the moon passes in front of a star from different locations on the Earth. And it reduced the uncertainty in that distance to the moon, or how high the moon, to about 2 miles, plus or minus 2 miles, based on telescopic observation. And in 1957, they used a new trick with the advent of radar, a product of World War II, looking for new uses for radar other than war on it. They tried shooting a radar beam at the moon. Sure enough, they got a return back. It bounced off the moon and came back. And by measuring the time it took for the radar beam to go out there and come back, they could get a pretty close idea how far the moon was away. And they got the distance within about less than a mile that way. Improved upon the optical measurements. And then in 1962, there was another idea. A group at MIT shot.
My dad built the instrument they used to measure the distance between the Earth and the moon with a laser.
And they think of just.
He talks about Perkin and Elmer. Well, Person Optics had a subcontract with Perkin and Elmer to build the instrument.
Moon through a 12-inch telescope and got them back. Looked at the moon through a 48-inch telescope and just barely could see it. They had to shoot a lot of laser bullets up there. Finally, they saw one hit. They didn't get very good measurements of it, but in 1964, the Russians tried a similar experiment, and they used a much bigger telescope, a 104-inch telescope, both to transmit the beam and to receive it. And they had good results, and in 1965, they refined the method using, for the astronomy buffs in the audience tonight, they used 50 nanosecond pulses, Q-switch ruby radar. And they established the lunar distance to 600 feet. How high the moon? Within 600 feet. Well, there was a fundamental limit that they were reaching there. They really couldn't do much better than that because the irregularities of the surface of the moon, some parts were higher than other. Look at mountains and valleys, craters, drills, bounce back at different times. You got sort of a smudge back when you saw the light coming back. And so you really couldn't do much better. A couple of years earlier, a well-known astronomer and his group at Princeton, and astronomers in the audience will know his name, Sir Dickey, had suggested that if you put a corner reflector on the moon, you could get rid of that trouble. And we'll talk about that in a little bit. In 1965, there was a group formed of people from different universities and observatories called the LURE Group, L-U-R-E, which meant Lunar Ranging Experiment Group. And the chairman of that group was a professor from the University of Maryland named Carol Alley. And they actively went to work on building an experiment to measure the distance to the moon. Well, I started by saying that throughout history, man has been interested in the moon, and it has been used to understand our whole universe. And I want to point out that that's particularly true with this specific experiment, since it can have good accuracy at measuring the distance to the moon. You can compute a lot of other things that are sort of interesting. Obviously, you can compute the lunar ephemeris, or the orbit of the Earth around the orbit of the moon around the Earth. You can determine the mass distribution of the moon. You can even make measurements of things here on Earth, like one popular one is called the continental drift theory. Some of you have heard about that. The theory that says the continents are actually, some are drifting apart and some are drifting together very slowly. And you can measure that rate by making measurements on the moon. And we'll talk about that a little bit later. You can make measurements of the changes of the location of the North Pole. Some of you have heard of the wobble of the North Pole, or the Chandler wobble. Some of those can be measured using this experiment. And even a far out one, we usually assume that the force of gravity is constant. And some people have proposed that it may not be. That gravity may be, in fact, slowly changing with time. This is an experiment by which you can check whether that idea is true or not. I've heard it said that people who should know that there are more possibilities for Nobel Prizes in this single, simple experiment. And in any others, or combination of any others, in all the manned and unmanned space programs. Well, of course, the heart of the experiment has got to be this corner reflector. We haven't got a corner reflector up on the moon yet, so we can't make any of these fancy measurements. What is a corner reflector? Well, this is a corner reflector. It's a three-dimensional version of the corner of a billiard table. You all know that if you get a billiard ball into the corner of the billiard table, in English on it, it'll come back, it'll make two bounces and then come back exactly parallel to the way it went in. The same thing is true of this three-dimensional corner, and you can try it yourself if you doubt it by going to any corner with a tennis ball and throwing it into the corner from any angle and see if it comes back to you. And I was going to prove that, but unfortunately my tennis ball ended up overboard. Anyway, this is where the same way tennis balls will bounce and billiard balls will bounce, light beams will bounce. And you can try that with three mirrors if you like, and a light and a flashlight. And it's the same kind of device that's used in the reflector on a bicycle, or used in stop signs where they want you to be able to read the letters, corner reflectors. Except this corner reflector to go on the moon had to be a very good one. One of the problems on the moon is that they've got big wide temperature spread from day to night. It is about 500 degrees higher in the daytime than the nighttime. And glass has to be treated pretty carefully so you don't get much distortion in that case. So NASA provided some money to get good corner reflectors and try to understand it. And those tests showed that you couldn't put a metallic mirror-like coating on the back because thermal gradients would be too tough and you'd get a lot of distortion. And the internal reflection at large angles would make difficult problems. And for the serious astronomers, just a word, the final design was silica, homogeneous fused silica. It was designed by like a little company and built by Merck and Elmer and with Buxton Beal Company. And a corner reflector has got a couple of characteristics that we have to remember in order to understand this story. This corner reflector, if it's mounted on the moon, is going to be moving. So if you shoot a light beam up to a moving target and it bounces back to Earth, it's not going to come back at the same place where it left, even though the light beams are fell. This is something which the amateur astronomers can explain to those of you who aren't. It's called velocity aberration. If you have a perfect corner reflector and shoot a light bullet up there, and when it comes back and hits the Earth, it'll be displaced about 1 mile from where you shot it up. Of course, we don't have perfect reflectors, so it turns out that if your corner reflector is bigger than 5 inches, that'll be what's happening. You'll have the return come back
They
in
were
your
about
place
this
and
way
you shot your
around.
bullet up.
It was in a
Usually
way
the
over
one is about an inch
how
and a
many
half
they
to
were.
5 inches.
They built it in
The
a big
return
spray.
pattern will be
You know
so
things
quick,
that,
so
that
the
they
fuse
use for
will go back and hit the
some
place
areas
it's shot.
use now, them little
So
prison,
that,
little light prison things, that's
reason,
a corner reflector.
NASA chose the little one, namely an inch and a half, to be the size, so they could use the same place for shooting the pulses up and getting them back. And then they measured. They set it down into a big block so the sun couldn't shine on it. And they also mounted it in Teflon so that it could handle these high temperatures. And you might think that if you had a really good corner reflector like this, it would be very insensitive to pointing, and I just want to show a slide here that shows why that's not true. And I know those in the back can't read this, but I can make the point, I think, without. This is just a curve of percent efficiency, let's say, versus angle, so that if you come in right in the middle of the corner reflector, you get 100% of the light back. But if you get off just a little bit, why the amount of light you get back starts fading pretty quickly. And by the time you get out to 6 degrees, you're already down to only getting half of the light back. So you have to keep the corner reflector pointed within about 6 degrees or better if you want to have reasonable performance. Now, this is important because of the characteristic of the moon that you're all aware of, but probably haven't thought about. You know that when you look up at the moon, you always see the same face. You see the same old man in the moon up there all the time. Never see the backside. That means that if you're standing on the moon, looking up at the Earth stands still in the sky. It doesn't rise and set like the moon here. It just stands still. Well, actually, it doesn't quite stand still. It is, over a period of a month, it makes a little circle in the sky. And I'll show you what that circle looks like on this next slide. Here's right. This is just the middle of where the Earth ought to be. And if you look at a period over a month, it makes a big ellipse like this. And that ellipse is, you can't read that probably from out there, but it's 6 degrees, plus or minus 6 degrees wide, and plus or minus 6.5 degrees tall. And we have to keep this corner reflector pointed within less than 6 degrees, so that means we have to have it pointed right dead in the center all the time, or we're not going to get enough light back at Earth to measure. Okay, let's show the next slide. Okay, here's what the mirrors look like. And each one of these little circles is one of those 1.5-inch mirrors. And since to get enough light back, we needed 100. So this is 10 by 10, 100 1.5-inch mirrors, and it's about 2 feet square and 1.5 foot high, something like that. Next slide. And it's adjustable so that you can get the proper angle so it can look at Earth. And it has a bubble level on it so that we could get a level, and then a shadow so that the sun shadow could be used to properly point it by using the shadow for direction within it. We have to get it within 1 degree now. And the reason I mention mention this, bring this point up, is that this was my job and why we're talking about it tonight. I'm not an astronomer by trade. My job merely was to point the mirrors closely enough so that the Earth could see them within 1 degree. And let's see the next slide. And here I am trying it. This suit is very difficult to work in. They've gotten better in recent life. At this time, in order to do something that looks like, one of my colleagues said, it's like Frankenstein trying to play Chinese checkers. It's very immobile and hard to operate. It's very difficult to see straight down. In fact, you can never see your feet. It's very difficult to see to put the instrument in place properly. Next slide. And here's the picture I took of the reflector, the set of mirrors, in place on the moon. We wanted to have a nice big flat rock table to set it on, so that it'd be perfectly level and wouldn't move in the years to come when it was being used, and we couldn't find a big rock table or any kind of table. We couldn't find a big rock that was level, so I just had to put it into the sand, and I worked it around until it seemed like it was pretty solid, and leveled it, and we did get it level, and we think it's pointing at Earth within less than a half a degree. It's the center of the mirrors. And now a little point here. The astronomers back here on Earth were ready to shoot their lasers at those mirrors just as soon as I got it out there. And they really wanted to zap me. They had three zappers ready. There was a 60-inch laser telescope out near Tucson, Gallup lens, the side of our telescope, and then the Texans down at Fort Davis, they had the McDonald Observatory's 107-inch telescope was ready to zap me. And out in California was the second biggest telescope in the U.S., the 120-inch Lick Observatory was ready to zap me too. Now, I wasn't too enthusiastic about that. I really didn't think I wanted to go down in history as the first man to ever get zapped over interplanetary distance. But I could understand why they wanted to shoot. You see, right back over here, not very far away, is the lunar module. And when it took off, its rocket exhaust was going to pick up a lot of dust, and that dust might get on the mirrors. And if it got on the mirrors, why, we might not ever be able to get any measurements made. So I was real careful about how I placed that so that it was pretty well protected against the exhaust, and we thought it would be clean. There was little trouble back here on Earth. The lasers are pretty powerful. Like ones they use are like 7 joules. And out there in California, Lick Observatory, which is on top of Mount Hamilton, some of you might know, it's pretty close to San Francisco. A lot of airplanes fly over there. And they didn't want to shoot that laser up through an airplane because they just put a nice clean little hole through it. And the president was just a little wild about that. Try to clear all those airplanes out of the way. It was a bad time for seeing. The sun, or the moon was pretty low in the sky, and there was a lot of turbulence and clouds, and just kind of bad. But they zapped anyway, and they didn't hit anything. There was a reason for that. They didn't know where I was. There was a reason for that, because I didn't know where I was. You all remember that some of you will remember that during Apollo 11, during the final phase, we had some computer problems because we made some final descent manually. During that time period, I lost my fiddling around with the computer, couldn't look out the window. So I kind of lost my reference. And our navigation wasn't all that good anyway, and we ended up being some distance away from where we had intended to land. And so when we looked out the window after landing, we didn't know where we were. We couldn't recognize any of the landmarks. So we didn't know exactly where to point out. It's been something to say that I did that deliberately. Acted on it. I didn't know where I was. Just so they don't forget. That's what I wanted to say. Okay, now this part gets a little bit heavy, but I want to show you what it looks like back in our this little white X in the bottom is where we were supposedly landing, somewhere around there. This little crater here is the crater Moltke, and this is Sabine and Ritter up here. This is the Sea of Tranquility, and this point to here, I think about 80 miles. And so he has to point that within a mile. You know, the spot that he's shooting up there is only a mile wide. And so that's just a little spot, and he doesn't know where I am. So they shot a bunch of times, shot, and they didn't get anything back. Finally, the weather was getting bad, and they just gave up for 5 days. In the meantime, I finally told them that's where I was. They figured out where I was, you know. One crew in my new location at the time, on top of Mount Hamilton there. They adjusted their equipment, they tuned up their laser, and they adjusted their telescope. And 5 days later, on the 1st of August, they shot again. And they shot 169 bullets up there, and they didn't see anything again. And then on the next one, they saw it. Do it. They tweaked up their machinery a little better, a little finer, and in the next 120 shots, they got 100 returns. 100 out of 120. They found me, for sure. And now I said there was a counter, and there were actually 12 little counters operating, each one for about half of a microsecond. They would start these counters just when they expected the light beam to get back, and the kinds of information they got will show on this next drawing. Shoot a light bullet up, and then let's say shoot. Here's how it goes: 5, 10, 15, 20 shots. After 20 shots, here's what they had. The first counter, it counted 2 returns. The next one 1, the next one 2, the next one 4, 2. This one right here, see it's kind of 10. That's when most of those got back, right there. So they knew within a half a microsecond when the light got back. And then there was 2, 2, 3, 1, 2. Okay, 10 shots. So it's pretty evident that we were indeed seeing the light that was shot, and not just some background light or somebody flashing a flashlight on the moon or waving or something like that. It was really the pulse coming back. Now, I want to look at a couple of these series of shots in time. So let's look at the next one. That one is this one right here. That was at 11 p.m. A couple times earlier, they've gotten this one. And this is the same kind of thing, bent 90 degrees down. You can see the big blob indicates when they think the time of the returning pulse was. And this is time up and down this way. And 0 time is just exactly when they expect it to get back. And you can see at about 11 o'clock, well, down here at 10:30, they were getting back a little early. And the light pulses were getting up there faster, or it wouldn't quite as far as they thought. And about 11 o'clock it was right on, and by 12 o'clock they were getting back late. Of course, whenever you get back after 12 o'clock, it's late. Well, they looked at this average line through here and said, what could that mean? Is the moon actually getting farther away? And they thought about that a while and fiddled with their computers, and finally turned out that sure enough, the location they used for Mount Hamilton in their computations was wrong. They had used the location, latitude and longitude of the observatory that had been used ever since 1885, when the observatory was founded, and it was wrong. So the first night they did this experiment, they found out where Mount Hamilton really was. And that was the first example of how you might find out something about the Earth from a measurement on the moon. Here's a way that you could find out something about the Earth. Let's say this is the Earth at the bottom and the moon up there. And here you are right with the moon directly overhead, and you make a measurement of how far it is to the moon. And you can make that measurement. These first measurements they made that first night were to an accuracy of about 10 meters or 30 feet, or 20 times better than anything we had up to that time. And since that, with getting better measurements, better sized pulses, and better counters and things like that, they got that distance down to about 15 inches. They know the distance from a station on the Earth to a station on the Moon. Now, you might ask, who cares? But we were very interested because we were thinking about charging mileage on our expenses. Now, if you got that accuracy to 15 inches, and then 6 hours later, when the Earth had turned through 90 degrees and you were out here at the edge, you made another measurement. And if you made corrections for the moon's motion, then you could tell the radius of the Earth within 15 inches. And that's considerably better than it's been known before. So that's just one simple example. And so you could turn the slide off and the light back on. And I'd like to give you just a couple other examples of the advantages of measuring using the moon. Write these down. I'd be interested in it for the rest. I'll tell you what the numbers are. First one, of course, is the distance to the moon. I give three numbers here. The first one is, well, let's say P4. And then I'll give 2 for lasers, laser measurements. Before lasers and lasers. With before lasers, we knew that distance, as I said, maybe to about 500 meters, the average distance to the moon. With lasers, depending on what the accuracy is, that's going to be 75 meters for a meter and a half accuracy. And if you have the good bullets in, put your good bullets in, you can get that down to maybe 30 meters, something like that. A couple of things about the Earth. Let's say the rotation period of the Earth, and what is that length of the day? How long is the day? You know that based on our current measurements, you know that accuracy to 5 thousandths of a second. That's 5 times 10 to the minus 3. 5 thousandths of a second. With the lasers, It's not quite so good with your bad bullets. It's about 10 thousandths. But with your good bullets, you can get that to about 1 10,000th of a second. Ten thousandths. This is 1. Okay, so we talked about the distance down to the axis of the Earth. That was the slide we gave. That's the Earth's radius. Earth's radius by before lasers was known to, get this right here, 10 meters. 10 meters was the distance. With the bad bullets, 3 meters. With good laser bullets, about 3/10 of a meter, about 30 centimeters. 3/10 of a meter. And there's a lot of other things. Motion of the pole, that's known to about 2 meters now. The wobble of the pole. And with the good bullets, you could get down to about 15 centimeters. And continental drift, we talked about that. It's an interesting one. Let's say you made measurements for 5 years. How big of a drift would you measure? Before lasers, you could make drift, continental drift, about 50 centimeters per year. In other words, if you made measurements over a 5-year period, you could detect 50 centimeters per year. With the bad bullets, about 30. And with the good bullets, 3. Get down to 3 centimeters per year if you measure in 5 years. Or to put another way, how long would it take you, let's say, to detect 10 centimeters per year? Let's say a warning we're drifting toward Japan at 10 centimeters per year. How long would you have to take measurements to decide that? Well, by our old, before lasers, about 30 years. 30 years of measurements would detect 10 centimeters per year. With the bad bullets, 15 years. With the good bullets, year and a half. Well, what that tells us is that if we use up our good bullets making these kinds of measurements, we should know about the continental drift for a few years by making measurements of the limits. Well, I hope that in this little, what I consider to be a technical discussion and an academic lecture, that I've convinced you you can learn some surprising things from them. And there's very much for our civilization to gain by pursuing this further. I thank you all for your attention. I look forward to seeing you again.